interference. When two waves come together, they can combine either constructively or destructively. Here's what I mean. If the first wave looks like this, and the second wave looks essentially the same, it goes up when the first wave goes up and down when the first wave goes down, we say they're in phase. They're waving together. And when they combine, the new wave looks just the same except it's twice as big. Okay, that's constructive interference. When you have the two waves that are essentially the same as before, here's our blue wave, and except our red wave is out of phase. And that means it goes down when the blue wave goes up and up when the blue wave goes down. We say these two are out of phase, and when they combine, the resulting wave is just flat. The two waves cancel each other out and leave no wave at all. Let's see, there's a lot of times that we see constructive and destructive interference. One example would be when we look at a soap bubble, or this lower picture is oil on water. We see a lot of interesting colors. So where do those colors come from? When we have a thin film and we illuminate it with light, here I've got a blue light ray coming in, hitting the surface, and reflecting off the top. But some of it also goes into the thin film. Notice it gets refracted a little bit. It hits the bottom, reflects off the bottom layer, comes back up, refracts back out at the surface, and leaves parallel to the incident ray. Parallel to the reflected ray. So both of the rays start here, interact with the surface, and then come out at the same angle. So if you're up here observing, you see those two rays together. But those two rays traveled different paths. This one had a shorter path length. This one had a longer path length. And if the difference in path length is exactly one wavelength, then when it gets up here, this wave's going to look like this, and this wave is going to look like this. They're in phase. They interfere constructively, and you'll see, if this is blue light coming in, you'll see blue light coming out. If the difference in path length is half of a wavelength, then when this one has this waveform, this one's going to be just the opposite. And they'll interfere destructively, and the blue light isn't seen over in this area. So if, for example, we had white light coming in, all the colors of light, and through this interference, the blue light is being canceled out, being from destructive interference, then we get all the other colors except for blue, and the light will look yellow out here. Now, if the light comes in at a different angle, the path length through the film is a different length, so it'll cancel out a different color. That's why we see in our soap bubbles, we see different colors in different areas. Also in our oil film, the different colors represent different thicknesses of oil on top of the water. So, Huygens principle. Huygens principle says, every point on a wavefront can be considered as a source of tiny wavelets that spread out in the forward direction at the speed of the wave itself. The new wavefront is the envelope of all the wavelets that is tangent to all of them. So, think about wavefronts coming in. These are maybe waves in the ocean, ripples in the ocean. We can take this wavefront and consider it to be a whole bunch of tiny wavelets. Every point, I can't draw every point, but every point along that wavefront a new wavelet starts. And those wavelets go out in all directions equally. I'm not drawing them quite right. There we go. So at each point, a wavelet starts, and the new wavefront after a certain amount of time is tangent to all of these little wavelets. So the wave has traveled, I'll use a different color. The wave has traveled this far, okay? In this case, thinking about Huygens' principle doesn't really change the way we think about the wave. We can also think about a wave that starts at a single point. Maybe you're dropping drops of water into a pool of water. Those wavefronts go out in all directions, just like our little wavelets. That's not very round. Oh, that's a little better. We can think of this wavefront as being composed of lots of little wavelets. So each one spreading out in a big circle in the forward, well, in a almost half circle in the forward direction. You get the idea. There we go, almost like a flower. Now if I draw the line tangent to all of those wave fronts, I'm going to end up with a larger circle, which is my new wavefront, which is what you'd expect when you have, when you drop drops of water into a pool. You get wavefronts that move out in concentric circles. Let's think about how Huygens' principle comes into play when we're thinking about refraction. Oh, we want that to be blue, light blue. Say we have a ray of light going, or a wave front going from air into water, for example. We have the incident, that's not what I wanted to do. We have a pen, there we go. We have the incident ray coming in at an angle perhaps like that. And that ray consists of these wave fronts that are like this. Okay? So each point on the wave is a new wave front. It's traveling out, but this one, as it goes into the water, is going to slow down. So the little wavelet here maybe travels this distance. The little wavelet here travels that distance. Same distance, right? All of them travel the same speed until they reach the water. Now this is going to travel fast here and very slow once it hits the water. So this new wave front is going to be parallel to the old wave front, but then bend once it gets into the water. I've exaggerated it. Let's draw the next one. It's traveling that far, all of these traveling the same distance, and then this one travels a much shorter distance, as does this one. So the wavefront inside the water is like this. Outside the water, it's parallel. See, we have these parallel wave fronts outside the water and these parallel wave fronts, and then the next one is going to look something like this, and then this. Well, that's not a very good one. Let's redo that. Okay, so you can look, if you want to say what's the direction of the light that's traveling through the water, it's going to be perpendicular to these wave fronts, or in this direction. So see, it's changed from this direction, and now it's traveling. Let's draw it in black. well, we'll make a different color that'll, well, black works. Now it's traveling that direction. That's refraction. That's the bending of light as it goes into a medium with a different speed of light. Now interference. If we have a wave front coming in, say it's just parallel wave fronts, planar wave fronts coming in, and we have an obstruction. Say we have a screen with 2 holes in it. The wavefront that comes, as it comes up to those holes, is going to be, well, we'll use blue. It's going to be a series of tiny wavelets. We'll say 1 at each of those holes, and it expands in concentric circles. And this one expands in concentric circles. Where the 2 meet in the middle, you'll see there's places where they're going to interfere constructively and places where they're going to interfere destructively.